Imagine standing near an erupting volcano. The ground shakes, rivers of molten lava pour down the mountainside. And then, suddenly, something impossible happens. Lightning, crackling and brilliant, erupts from inside the volcanic plume itself. Not from storm clouds miles above, but from the volcano. This isn't science fiction. This is volcanic lightning, one of nature's most spectacular and mysterious phenomena. And today, we're going to uncover exactly how volcanoes create these shocking lightning storms. Welcome back to the channel. If you're new here, we explore the most mind-blowing phenomena in nature and science, breaking them down so anyone can understand them. And trust me, what you're about to learn will change how you see volcanoes forever. Now, volcanic lightning is rare, powerful, and honestly looks like something straight out of a fantasy movie. But the science behind it, that's even cooler. So let's dive in and answer the big question. How does a volcano make lightning? Before we get into the science, here's why this matters. Understanding volcanic lightning isn't just about satisfying curiosity, though that's a huge part of it. Scientists study this phenomenon to better predict volcanic eruptions and understand the incredible forces at play during these events. Plus, if you're someone who loves learning about the natural world, this is exactly the kind of thing that shows just how wild and interconnected everything really is. And speaking of curiosity and learning, if you want to keep exploring science in a hands-on way, check the description below to download our ebook packed with 50 DIY science experiments and fascinating facts. It's perfect for anyone who wants to take their love of science beyond just watching videos. But right now, let's get back to these electrifying eruptions. So, what exactly is volcanic lightning? Let's start with the basics. Volcanic lightning, also called dirty thunderstorms, is a weather phenomenon where lightning occurs within or around a volcanic plume during an eruption. Unlike regular lightning that forms in rain clouds, this type of lightning is generated by the volcano itself, specifically within the massive ash cloud that gets blasted into the atmosphere. You might be thinking, wait, how can a volcano create lightning? Isn't lightning caused by storms? Great question. The truth is, lightning happens whenever there's a buildup of electrical charge that needs to be released. In a regular thunderstorm, that charge builds up in clouds. But in a volcanic eruption, the ash cloud acts like a giant storm system, and the conditions inside that cloud are perfect for creating lightning. The first documented observation of volcanic lightning dates back to the eruption of Mount Vesuvius in 79 AD. That's right, the same eruption that buried Pompeii. Ancient Roman writers described lightning flashing within the volcanic cloud, but it wasn't until modern times, with high-speed cameras and scientific instruments, that we really started to understand what was going on. All right, now for the good stuff. How does this actually work? Let's break it down step by step. When a volcano erupts, it doesn't just spew out lava. It also ejects massive amounts of ash, rock fragments, gas, and water vapor into the air at incredibly high speeds. We're talking about particles ranging in size from microscopic dust to chunks of rock, all being thrown into the atmosphere at hundreds of miles per hour. As all these particles collide with each other inside the eruption cloud, something fascinating happens. They exchange electrons. Some particles become positively charged, while others become negatively charged. This is similar to what happens when you rub a balloon on your hair and it sticks to the wall. That's static electricity, and it's the same principle at work here, just on a much, much larger scale. Now, here's where it gets interesting. These charged particles don't just mix randomly. The heavier, negatively charged particles tend to sink toward the bottom of the plume, while the lighter, positively charged particles rise to the top. This separation of charges creates an electrical field, and when the difference becomes strong enough, boom, you get a lightning strike. The electricity arcs through the ash cloud, trying to balance out the charge, and we see it as a brilliant flash of light. But wait, there's more. Volcanic lightning actually occurs in 3 different forms, and each one is fascinating in its own way. First, there's the lightning that happens right at the vent, in the very first moments of the eruption. This is when the magma is being violently fragmented and blasted out of the volcano. The sheer chaos of that moment, with particles colliding at extreme speeds, creates immediate electrical discharges. This type of lightning is usually the most intense, but also the hardest to observe, because it happens so quickly and in such a dangerous location. Second, there's the lightning within the main eruption column. This is the type most people think of when they picture volcanic lightning. The ash cloud, rising thousands of feet into the air, becomes a massive electrical generator. As the plume rises and spreads, the charge separation we talked about earlier creates multiple lightning strikes that can last for minutes or even hours. This is where you get those incredible photographs with dozens of lightning bolts streaking through a towering ash cloud. Third, there's the lightning in the umbrella region. As the eruption column reaches a certain height, it starts to spread out horizontally, forming what looks like an umbrella or mushroom cloud. In this spreading region, the turbulence continues, and so does the charge separation. This creates a different pattern of lightning, often spreading out across a wider area of the sky. Each type tells us something different about what's happening inside the eruption, which is why scientists are so interested in studying them. So why do scientists care so much about volcanic lightning? Well, it turns out that studying these electrical discharges can actually help us predict and understand volcanic eruptions better. For one thing, the intensity and frequency of volcanic lightning can tell us about the size and violence of an eruption. More fragmentation means more particle collisions, which means more electrical activity. By monitoring the lightning, scientists can gauge how explosive an eruption is becoming in real time. Lightning also creates radio waves that can be detected from far away. This means that even if a volcano is in a remote location or visibility is poor, scientists can still monitor the eruption by tracking the electrical activity. It's like having an extra set of eyes on the volcano. Plus, studying volcanic lightning helps us understand atmospheric electricity in general. The same principles that create lightning and volcanic plumes apply to other phenomena, from dust storms on Mars to the formation of thunderstorms on Earth. It's all connected. Now, you might be wondering, if this is so useful, why don't we know everything about it already? Well, studying volcanic lightning is incredibly challenging, and here's why. First, volcanic eruptions are unpredictable and dangerous. You can't just set up equipment next to a volcano and wait for it to erupt. Scientists have to rely on remote instruments, cameras, and sensors that can withstand extreme conditions, and even then, equipment can be damaged or destroyed by the eruption itself. Second, volcanic lightning happens fast and in harsh environments. The ash is abrasive, the gases are toxic, and the conditions change rapidly. Getting clear measurements requires specialized equipment and often a bit of luck. Finally, each volcano and each eruption is different. What happens at one volcano might not happen at another. This makes it hard to create universal models of how volcanic lightning works. Scientists are still piecing together the full picture, eruption by eruption. But that's what makes it exciting. Every new eruption is a chance to learn something new. Here's a question that might be on your mind. As climate patterns change and volcanic activity continues around the world, could we see more of these events? The short answer is, it depends. Volcanic eruptions are driven by geological processes deep within the Earth, and those aren't directly affected by what's happening on the surface. However, the way eruptions interact with the atmosphere could change. For example, if there's more moisture in the air, that could affect how ash plumes develop and how much lightning they produce. Scientists are also getting better at detecting and documenting volcanic lightning thanks to improved technology. So even if the frequency of eruptions doesn't change, we'll probably see more incredible footage and data in the years to come. Either way, volcanic lightning will continue to be one of nature's most awe-inspiring displays. All right, let's wrap this up and bring it all together. Volcanic lightning is created when particles in an eruption cloud collide and exchange electrical charges. The separation of these charges creates an electrical field, and when the buildup is strong enough, lightning strikes through the ash. This phenomenon comes in three main forms, from the initial explosion at the vent to the spreading umbrella cloud high in the atmosphere. And it's not just beautiful, it's scientifically valuable, helping researchers understand eruptions and improve monitoring techniques. The next time you see footage of a volcanic eruption with lightning crackling through the ash, you'll know exactly what's happening and why. It's a reminder of just how powerful and interconnected the forces of nature really are. Volcanoes don't just reshape the landscape, they can literally electrify the sky. If you enjoyed this deep dive into volcanic lightning, make sure to hit that like button and subscribe for more incredible science content. Drop a comment below and let me know what natural phenomenon you want us to explore next. And remember, never stop being curious about the world around you. Thanks for watching, and I'll see you in the next video.